It's a pleasure to introduce our next speaker, which is Shruti Puri, who will tell us about noise-tailored quantum error correction for next-generation qubit technologies. Thank you. Please take it away.
Hi, everybody. I'm so happy to be presenting this talk to you guys. I wish I could be there in person, but oh well. Just a quick question before I go ahead. Can you see my cursor?
Yes, we can.
Awesome, great. And don't if you have some urgent questions, don't hesitate to stop me in the middle. Okay. Before starting my talk today, I would like to thank the error correction team at Yale, as well as our old and new collaborators. So today I will be talking about how to think about scaling up quantum error correction in a way that you are able to exploit the noise structure in your qubits for better error correction. So the main message of the talk is that not all types of errors are equal. Some errors are more contagious and spread rapidly through the circuit, while there are other errors that are easier to detect and correct. So maybe when you're designing error correction codes, or when you're designing your new qubit systems, you should think about developing it in such a way that you want to suppress the most contagious errors, even if that means maybe slightly increasing the errors that are nonetheless easier to detect and correct. Okay, so with this, let me first establish the language that I'll be using. So if you think about qubit errors, you can decompose it in terms of bit flips. So that is like the action of the poly X operator on your state. You can think about phase flips, which is the action of the poly Z operator on your state. And you can have Y error, which is both a bit flip and a phase flip. On top of this, you can have continuous errors. So it is basically a superposition of the poly operators. You can also have a type of error, which we call erasure. Now, what is an erasure error? Erasure error is basically, you can think about it as qubit loss. So you know that the qubit is lost or something bad has happened to your qubit, but you're not exactly sure what has gone wrong. So that kind of error is called as erasure. There's also a type of error that is leakage. So the qubit basically leaves your computational subspace, but you don't know that it has left the computational subspace. You don't know about it. So the difference between leakage and erasure errors is leakage is you don't know that something bad has happened, whereas in erasure errors, you know something bad has happened. Okay, and I will. So most of the times when we think about these poly errors, we think about depolarizing noise, such as the rate of bit flips, phase flips, and Y errors are equally likely. But there are many physical qubit platforms in which one type of error, such as a Z error, is more dominant than other type of errors, like the X and Y errors. And such qubits are known as biased noise qubits. So these qubits preferentially couple to the environment along one axis of the Bloch sphere. And in this case, you can define three different probabilities of errors, Z, X, and Y. And we have probability of Z errors much, much greater than the probability of X and Y errors. And we can define this ratio, which is the bias, which is much, much greater than 1. So in my talk today, I will tell you that if you have biased noise qubits, or if you have qubits in which erasure is dominant, then you can reduce the threshold requirements for quantum error correction. Okay, so firstly, I will begin with the what is called the XEZX surface code for biased noise. So just like the regular surface code, in the XEZX surface code, you have a 2D lattice of qubits arranged in the manner that I've shown. The stabilizers of the code are the 4-body XEZX operators acting on the 4 qubits around each of the plaquettes. The logical Z operator is the poly Z acting on the qubits across this red line. And the logical X operator is the product of X operators acting on the qubits across this blue line. Now, in order to measure the stabilizers of this code, what you do is you place an ancilla qubit at the center of each of the plaquettes, and you'll do a series of control NOT and control phase gates between the data qubits and the ancilla qubit, and then you'll measure the ancilla qubit. So the ancilla qubit was measured in the same state that it began with, then the stabilizer value was +1, otherwise it's -1. So in this Nature Communication paper, it was shown, which introduces XZX surface code, it was shown that the XZX surface code has a high threshold if your errors are biased. So in this talk, we'll be looking at Z-biased errors. So a probability of Z errors are greater than X and Y errors. So this is a figure from the paper, which plots the threshold versus the bias. As the bias increases, that is, you get you're suppressing X and Y errors more and more. The threshold increases and goes up to around close to 10% for infinite bias. And the red dots are the threshold when you're using the regular surface code and you have bias noise on top of it. Okay, so these thresholds were derived were evaluated under a phenomenological noise model, which basically says that you have some errors on your data qubits, you have errors on the ancilla, and basically you have measurement errors, but all the gates in between that you're actually doing between the data and ancilla qubits are perfect. So the interesting question, though, is what happens when you think about circuit level noise, like when you allow errors to happen in these gate operations themselves? Okay, so remember, this is the gate set that I'm trying to do. So let's look at what happens when you try to do a control phase gate. If you try to do a control phase gate between your data qubits and the ancilla qubit, you'll try to establish a kind of a ZZ interaction between the two. In this case, if you show, you can easily show that if there is a Z error, which is a dominant error on the data qubit, then a Z error commutes with this Hamiltonian at all times, and a Z error propagates as a Z error on the data qubit. However, a Z error on the ancilla qubit, and similarly a Z error on the ancilla qubit also propagates as a Z error on the ancilla qubit, and the noise channel of the control Z gate is biased. That is, the dominant error propagate only as dominant errors in the system. Similarly, you can show that the errors in preparation and errors in measurements are trivially biased. Now, what happens though if you try to do the control NOT gate? In this case, you would try to establish an XZ type of interaction between your data qubits and the ancilla qubit. And if there's a Z error on the data qubits, you can show that because the Z doesn't commute with this Hamiltonian at all times, a Z error on the data qubit propagates as a linear combination of Z errors and Y errors on the data qubits. In fact, you can show that 25% of the Z errors are converted to Y errors in this. And therefore, the C0 gate unbiases the error channel in the sense that you're converting dominant errors to the less dominant errors. And so you don't have a biased noise system anymore, and you don't expect the code to show big improvements in thresholds. In fact, there's a no-go theorem which says that bias-preserving C0 gates are actually impossible in strictly two-level systems. Okay, so now to show you how a bias-preserving C0 gate does or does not impact the performance of the code, we will simulate the logical error for the code for different values of the Z errors for a bias of 100 and extract the thresholds. In terms of the Z errors, the bias, and this is, I assume magically, the world has given me a bias-preserving control NOT gate. So in this case, the threshold in the circuit level picture in terms of the 2-qubit gate error rate is about 2%. Now I do the same thing using the standard control NOT gate which converts 25% of Z errors to Y errors. In this case, the threshold turns out to be 1.7%. So the threshold clearly decreases depending on if you have a bias-preserving C0 gate or not. But the decrease doesn't seem to be too much. So why should anybody care about this? Well, because of the way error correction works, a small change in the threshold can actually have a big change in the logical error rate. So here, if you look at, if you start with the same size of the lattice, for example, an 8x24 XZX code, then with the bias-preserving C0 gate, the logical error rate that you're going to get is about an order of magnitude lower than the logical error rate without the bias-preserving C0 gate. So what this is telling you is that what is important is not just the total error rate in the gates, but it's important for you to understand what are the dominant errors in the gate, and just changing the structure of the errors can impact the performance of your code a lot. So now you must be wondering that I just told you that there's a no-go theorem and there is no bias preserving C0 gate. So then why am I talking about this? Well, it turns out that if you have higher dimensional systems or continuous variable qubits like the Kirk-Cat qubit, you can have a bias preserving C0 gate. And in fact, in our paper, we have shown that with these bias preserving C0 gates in the Kirk-Cat qubits, you can get a threshold of about 6.5%. So indeed, we can have high performance codes if you think about exploiting the structure of noise in your system. I'm not going to talk about what these Kirk-Cat qubits are. If you're able to, you can still log into the AP's March meeting website and listen to all the updates on the experimental updates on the Kirk-Cat qubits in these two talks. We have actually not just a threshold. What we have shown is that with these Kirk-Cat qubits, you can actually also improve the fidelity of magic state preparation in the XEZX surface code. And I will refer you to this archive paper for those results. Okay, now the other error that I promised to talk about is the erasure error. So this was the work we did with Jeff Thompson's group in Princeton. So they work with atomic qubits, and they choose the computational space that I've highlighted here in some atomic level of some ytterbium atoms. And they do the gates such that most of the errors are actually leakage, but those leakage errors can be detected in your system. So the idea is that when you try to do gates, you couple your computational states to a excited Rydberg state, and the dominant error is the Rydberg state decaying to another level, and you can do a fluorescence measurement to actually see if this decay has happened or not. And so most of the errors in this case are then erasure errors because we're able to detect them. But we just don't know what kind of error it was. However, just this fact that you know an error has happened actually also leads to an improvement in the threshold. So we showed in our paper that if you have about 98% of erasure errors, then the threshold for the surface code becomes about 4.15%. Okay, so now I'm going to quickly change gears a little bit and talk about our recent results on measurement-based quantum computing with bias noise. Okay, so most of the time we're used to thinking about circuit-based quantum computing, in which you have, your qubits are in some initial state and they're just sitting fixed somewhere on your chip. And you're doing gate operations on these qubits in time. And at the end of the circuit, after some time, you get some output state. Now, you can also do this in a measurement-based model. In this model, you again start with the two qubits you care about, but you add extra qubits into your system. And then you locally entangle these qubits using 2-qubit control Z gates. Now you measure each of these qubits. So this state is actually called the cluster state. And now what you do is you actually go and measure each of the qubit in some bases that you have precompiled. And after you do that, these qubits that you have measured disentangle from the cluster, and you're left with these two states, these two qubits, and the output state of these qubits is the same as if you did a unitary transform on the input state. So this is measurement-based quantum computing. So a few facts here that if you have, you can do universal quantum computation if you have a 2D cluster state and these operations using measurement-based model. And if you can do a universal fault-tolerant quantum computation if you actually have a 3D cluster state. Now, you might wonder why I care about measurement-based quantum computing. Well, I care about it in certain platforms such as photonic qubits, where you want to measure photons very quickly after they're generated, because otherwise they're going to be lost from your maybe fiber or something. In other cases, this might be useful as well, especially if you have limited hardware operations that you can do. So like, for example, if you don't have gates, but you have really good measurements, then this is probably what the measurement-based model is probably what you should use. And we are currently actually working on some superconducting bosonic qubits in this measurement-based model. Okay, so it turns out that any stabilizer code can be converted to a fault-tolerant cluster state with a process called as foliation. So the question that we asked was, can we foliate the XZX code or another stabilizer code that has high threshold to bias noise and get a corresponding cluster state that also has a high threshold to bias noise? When I first asked this question to some of the experts in the field, the answer wasn't clear, and it seems like this couldn't be done. But then I gave the problem for my postdoc, Jehan, to solve, and he did it. And so we are now able to come up with a new foliation procedure such that you're able to foliate the XZX code into a cluster state, which also has a high threshold against bias noise. Okay, so let me explain this a little bit further. So firstly, let me explain why the standard foliation procedure doesn't work, and why using the standard foliation procedure, I couldn't just convert the XZX code to a high bias noise threshold cluster state. Okay, so firstly, this is the notation I'll be using. So these qubits as dots are initialized in the plus state. If you have a line coupling, edge coupling these two qubits, you're doing a control Z gates, and a box is an X measurement. So firstly, let's just think about a 1D cluster state and teleporting a single qubit through the 1D cluster state. So you initialize your qubit in the state that you want. You add more qubits to your control Z gates, and then you measure for the first two qubits in the X spaces. So you get some measurement outcomes X1 and X2, which can be 0 or 1. So you can easily show this, that the output state is the same as the input state, but with some poly corrections to it, which depend on the measurement outcomes. Now, this is just a short teleportation state, but you can also have a longer teleportation state where you have when you add more physical qubits and, again, measure all of these qubits except the last qubit in the X spaces, and the state of the last qubit is just the input state up to some poly corrections. Now, what you might want to do is, as you're teleporting the qubits, you might want to measure their stabilizers and check for some errors. So for example, you might want to, say, implement a repetition code, just as a simple example that I can actually draw for you. So in this case, you start with these three states that you're teleporting through the 1D cluster state. And then you're going to just add these additional qubits at the center, like shown. And now you'll measure all of these qubits in the X spaces. And in fact, the measurement outcome of these center qubits actually tell you about the X1, X2 correlations between this 1D state, this 1D cluster and this 1D cluster. And similarly, measurement outcome of this qubit over here tells you about the X2, X3 correlations between this 1D cluster and this 1D cluster. So in this way, you can actually measure the stabilizers as you teleport them through the 1D clusters. Okay, now let's think about what happens if I have dominant Z errors in my system. So if I have Z errors in my system, then it's going to affect the X measurement outcome. So say there was a Z error on this qubit and it affected the X6 measurement outcome. That means that you misread this X6 and you actually accidentally did an incorrect poly X correction on your state. So this means you're actually converting a physical Z error to an X error on your state. And therefore, this foliation procedure actually doesn't preserve the bias. And if you have bias noise qubits, you should not use this foliation procedure because it's not going to help you. So what did we come up with? How did we solve this problem? So we basically changed the foliation procedure, and to understand that, this is the new legend that I'll be following. So now I have two types of qubits, one that we call the X-type qubit, which is initialized in the plus state, and the other which we call a Z-type qubit, which is initialized in the 0 state. And if you have an edge between two X-type qubits, you do a control Z gate. And if you have an edge between a X-type and a Z-type qubit, you'll do a control X gate. Importantly, this is only a one-way control X in the sense that your control is always going to be on the X-type qubit and the target is always going to be in the Z-type qubit. And now you're going to do a measurement, but importantly, the Z-type qubit will always be measured in the Z basis and the X-type qubit will always be measured in the X basis. Okay, so now let's see with this new technique, how can we teleport just a single qubit? So I initialize a single qubit in some input state, and I add more qubits alternatively, which are X-type and Z-type qubits, and I do my gates. The way we are doing the control X gates, all the control X gates are actually commuting, so you can actually do them at the same time if you have the ability to do that. Okay, so once I form this 1D cluster, I'm going to measure the Z-type qubits in the Z basis and the X-type qubits in the X basis, and you can show that the state at the output is again some Pauli corrections to the input state. Importantly, now what has happened is that in this cluster state, the physical Z errors do not convert to X errors. So physical Z errors will only affect the measurement outcomes of the X-type qubits. That means they'll only affect X2, X4, X6. And those measurement outcomes, those measurement outcomes only apply a Pauli Z correction to your input state. So that means a physical Z error can only cause a kind of a logical Z error on your teleportation state. The physical X errors, so physical Z errors do not affect the Z measurements. So they do not affect the measurements of these Z-type qubits. And therefore, you'll never be, so a physical Z error will never be able to apply a X error onto your state. So in this case, this teleportation technique preserves your noise bias. So again, now you can play the same game. If you want to check, if you say want to now have only Z errors in your system and you want to say do a repetition code, then you can take 3 such teleportation chains, add some additional qubits at the center like shown over here. And when you measure these qubits, according to this legend shown here, then the measurement outcome of this center qubit is going to tell you the X1, X2, and X2, X3 correlations in the 1D teleportation chain. So now you can adapt this to make the, to foliate the XZX surface code as shown. So I'm just showing the 4 qubits around each of these plaquettes over here, replaced by the 1D cluster state. And now you want to measure this XZX stabilizer. So you're going to now put qubits at the center, which are coupled to like the 4 qubits around it. And you might want to measure, you want to construct this whole whole lattice, so you'll add more ancilla qubits to measure these to measure the stabilizers as you go propagate in this cluster state. Now we can easily show that the product of the X and Z the product of the X measurements on these black dot qubits and the Z measurements on these Z-type qubits is actually 1 if there's no error. So that is your stabilizer of your cluster state. Also, a Z error on your on the X-type qubits will only cause defects in the plane, whereas an X error will cause a defect that breaks the plane. So if you only have Z bias noise, then your defects all lie in one plane, and so your decoding actually becomes easy, and that's why we actually get a high threshold. And so these are some simulation results for phenomenological noise. And on the top, we have the XZX code. On the bottom, with foliated, the XZX cluster state foliated with the new technique. And on the bottom, we have the standard cluster state, which is the RHG cluster state. And clearly, we see that as the bias increases, our threshold increases, whereas that doesn't happen in the RHG lattice. We can also do some more detailed circuit-based simulations. And again, we see that the XZX surface code actually does show an improvement when the bias increases. Okay, so I don't think I have a lot more time, so I'm going to stop here. But in our paper, we also discussed how to physically construct these circuits and what are some of the physical platforms which could benefit from such a cluster state. In fact, the most widely used hardware for the cluster states is photonic qubits, and the cluster state is made using using fusion measurements in photonic qubits, and those fusion measurements actually most naturally, in fact, give rise to the XCZX surface codes, and we have discussed this. XCZX cluster state, which we have discussed more in the paper. And in fact, the fusion failure, which is an important noise source in a photonic cluster, is also actually equivalent to a Z error in the system. So in fact, you can get, there's an opportunity to exploit this for even better thresholds. So I'm going to stop here and take more questions.
Thank you very much for the fascinating talk. So I'll now take some questions from the room or online. Any questions? Okay, it seems that there aren't any questions, so we'll thank you once again for the very nice talk.
Thank you.